Right, hello everybody. This is Robert Franke from Likat in Rostock, Germany. And I welcome you to the 5th event of the Sustainable Chemistry Lecture Series. And this time again, we have two excellent guest speakers. And it's my pleasure to welcome Xiaodong Zhu from Stockholm University. And she will show us how transmission electron microscopy can serve as a powerful tool for enabling green chemistry. Our second guest is Aryan Clay from the ICIQ in Spain. And he will provide some insights into the latest advances in catalytic CO2 utilization. Before we start with the program, I would like to make a few announcements. The first announcement is regarding our coming event. The 6th event will take place in on the 21st of June at 4 p.m. This is a Monday, and we will welcome Professor Walter Leitner from the Max Planck Institute for Chemical Energy Conversion in Germany, and he will talk about catalytic activation of green hydrogen for green chemistry. And our second guest will be Professor Roger Sheldon from Delft University of Technology, so the Pope of green chemistry, so to speak. And he will talk about engineering a sustainable economy with green chemistry and biocatalysis. So again, the 21st of June, please mark your calendar. And the link you find also on the UChem's website in the event calendar. All right, so before we start with the scientific program today, I will make some more announcements. Some general remarks. Some thanks go to UChem's and KVCV, which is the Royal Flemish Chemical Society, for supporting the lecture series. And a very special thanks goes to Thomas Franken from KVCV for his tremendous support. So he supports our guides, our series personally and also technically. And finally, a further remark regarding the discussion which follows the talk. I would ask all the participants of the workshop, the seminar, to use the Q&A option, which you find in the panel at the bottom of your Zoom interface, and post the questions there. And this can happen already during the presentation. Now I stop to share here, and while our first speaker prepares herself, I can take the chance, and it's my pleasure actually to introduce her. It's Xiaodong Zhu from Stockholm University. She's currently full professor there and the chair of the Inorganic and Structural Chemistry unit and deputy head of the Department of Materials and Environmental Chemistry at Stockholm University, as I said. So yeah, this is 3 roles in one person. Xiaodong received her master's in physics, coming from a slightly different direction than at Beijing University of Technology. Then she moved to Sweden, very long way, where she worked on her PhD in structural chemistry at Stockholm University. And after graduation, she went to Lund University for a postdoc, then returned to Stockholm, where she finally became full professor. And since then, she has been extremely active. She has published so far over 300 research papers, 5 patents in the field of solid state chemistry, structural analysis, and many other fields. And her research was very fruitful and rewarded also with numerous prizes. I will not read the entire list. I will only focus on 2 very prestigious ones. One is the Targa Erlander Prize, which is given by the Royal Swedish Academy of Science. And the other one I would like to mention or to highlight is the Svante Arrhenius Medal given by the Swedish Chemical Society. All right, so before the audience becomes impatient, I rather finish the introduction, and I would like to hand over to you, Xiaodong, please. Now the screen is yours.
Thank you very much. I would like to thank the organizers, Robert, for the kind introduction. And I will first share my screen. Would you please?
Oh, sorry, yes.
Stop sharing.
I haven't still. Now you should be able.
Yeah, okay. So let's see. I got some audio. Stop sharing other screen. Yes. Okay. Oh, sorry. Let's switch wrong screen sharing.
Looks good.
Yeah, we can see you.
We can see you.
Yeah. Can you see the screen?
Yes, we can.
Yes.
Okay, good. Thank you. So this is a very nice lecture series. I have been enjoying very much for participating. And I would like to say that I'm not really working closely to like green chemistry, sustainable chemistry. I'm mainly working on method developments and also develop new materials. So today I would like to show some of our recent results to see how to develop new materials that can be used as a potential for sustainable chemistry. And I would mainly talk about porous materials, nanoporous materials. And for those of you probably are not very familiar, and they have usually very high surface areas. This is the main property of the porous materials, like a swamp, that's what you see here. And if you look at their pores, and actually they have pore dimensions very, very close to the molecular dimensions. So in that case, they have a very high selectivity. And it has rigid architecture, which means you can use it as a nanoreactor, as a host, for storage and for like reactors for catalysis. And you can use these types of porous materials for separation. And they have a wide range of structure diversity. And so, which means you can actually make a designed functions and properties inside these porous materials. So there are large wide of applications. And I will mainly talk about two types of porous materials. One is related is zeolites, and another type is microorganic frameworks. My research have been working mainly focusing on developing new porous materials because different porous materials have different properties, and there is a need to have a large range of different types of porous materials. And so, for example, zeolites, different types. In this specific zeolite, we can have like chiral channels along the zeolites, which is very important for chiral separation, for example. And we have large porous materials with pores like more than 2 nanometers in size, which is also designed for porous materials, and the metaorganic frameworks. And it is built by metal clusters and organic linkers. When we have different porous materials, the first thing is how the structure look like. And this is important. And to determine the structure, and then we know their properties and functions. And to determine the structure of normal inorganic materials and organic compounds and up to proteins. And the basic, most common method is X-ray diffraction. And this is a database called Cambridge Structure Database. Like there are more than 1 million crystal structures in the database, and more than 5,000 new structures every year have been deposited. This is just a part of the structure organic crystal structures. And more than 90% were determined by single crystal X-ray diffraction. So X-ray diffraction is a very important technique for structure determination. But there is only one drawback of the method, and it needs large crystals. Large, I mean like a few micrometers in size in different dimensions, and for more complicated structures, the dimensions need to be larger. And to grow large single crystals, it's always a problem, and that prevented structure determination of many different new materials that probably have been synthesized, but was difficult to get to know their structure. And how we want to approach this problem. And we would like to use electron crystallography. Electron crystallography is used in electron microscopes and to study different materials. And we can study materials with called powder, so not single crystals. And for example, just a typical powder that's visible. And usually I think most of you have used X-ray powder diffraction to characterize the materials. X-ray powder diffraction can make phase identification of the materials, but sometimes it's very difficult when you have mixed phase and the structure is complicated. It's a lot of peaks. It's difficult to know what kind of structure it is. And because the powder pattern is only one dimension. And if you look at these powders in electron microscopes, and actually it behaves as a single crystal. And you can get the images and just look at the morphology, or you look at the high resolution images, you can look at the atoms. And you have also single crystal electron diffraction, as you see here. So this single powder and can be can diffract, behave as a single crystal. And so this is a advantage of using electron diffraction and electron microscopy. And if you use images, actually you can visualize individual atoms. And so this also means that it carried more information combined with electron diffraction. The reason is that what we call the structure factor phases that is really needed for obtaining crystal structures. They are already present in the image, can be directly obtained. And what we can use electron diffraction, electron crystallography is to study crystals that are too small or too complex for X-ray diffraction. So that is both for X-ray powder diffraction and also single crystal X-ray diffraction. How do we do that? If you have images, actually you can process this image and obtain both the amplitude and phases from the image. So this is actually make a Fourier transform of the image. And what you want to get is like the indexes of the reflections. You have HKL, Miller indices, and for each of the reflection, you have amplitudes. That is how strong this diffraction spot is. And also their phase information. And with this information, you can just need to make an inverse Fourier transform using this formula. So you have the structure factor, amplitude, and phases here, obtained from here, and make an inverse Fourier transform. You get this map with electrostatic potential that we obtain. And from this potential, you can identify atomic positions. In this case, the black spot corresponding to heavier atoms. So you can build a model. If you have electron diffraction data and the phase information is lost, so we only have the amplitude, we know their intensities. But it doesn't matter because X-ray crystallography has been developed for more than almost 100 years, and it is possible to determine the phases directly from the intensities. There are many different methods that have been developed for X-ray diffraction, but it can be also used for electron diffraction. So this is the basic principle of what we do. We want to get the structure factor, amplitude, and phases to finally find the structure. When you have high resolution images, and you can use only high resolution images or combine images and the electron diffraction. And we did that in the 90s already to show that it was possible to solve unknown structures using electron crystallography, we call it. And so images usually is very demanding. You need a very good microscope, and still you don't get very high resolution. And the electron diffraction is easier, and you can easily get a subatomic resolution, sub-angstrom resolution using electron diffraction. To combine these two techniques will be a very good approach. And if you have complicated structures and you need to combine images from different orientations. So this is an example of a zeolite that we combine images along these two different projections. What we do is we extract the amplitude and phases of each of these from each of these images. And in this case, actually, because the images are like contains a lot of disorder, as you see here, it's not really strict periodic. And with very, very small area, a few nanometers in size, it's already enough to get the amplitude and phases. And when you combine this information, you can get a beautiful 3D structure model of this zeolite. And so images approach, we usually early days we use this techniques, but it is very demanding. And to be able to solve such a structure usually requires like many months or years. And because it's very difficult to collect very good images. And and in the like 2000, beginning of the 2000s, several groups have developed 3D electron diffraction techniques. It's also called the micro-ED. And it is performed in a standard microscope. What you do is you have a crystal and you tilt the crystal in the microscope and you collect the electron diffraction data like a movie. And so arbitrarily oriented crystal, you just tilt it to collect the data. And so which means that you collect the data from all different orientations. And then later you combine this data and you get intensity of the crystal of all reflections. And there are different methods that have been named differently using slightly different techniques. And our group developed the technique called rotation electron diffraction. And how do you do? Actually, we wrote the software, we control the microscope, control the camera, and we rotate the crystal in the microscope. And so that is the diffraction pattern you see. And each diffraction pattern shows different orientation, and that gives different intensities and different reflections, which means if you start to tilt the crystal continuously, and you will be able to sample the whole, what is called the reciprocal lattice, that is the diffraction space. And by this, you will make another program that you can see here. You can combine all diffraction patterns from different orientations together. And now you can really see, okay, in reciprocal lattice, you have different diffraction spots, they have different intensities, and they form 3D periodic lattices. And using this, we can determine the unit cell parameters and the space group, and also to get the intensities from these diffraction spots. And what it is used for with this information, and you can make phase identification, because from the unit cell space group, you know which phase is probably yours crystal corresponding to. And if it is unknown phase, and you can use the intensities extracted from the image, and also like unit cell parameters to determine the crystal structure in the same way as you are doing for the single crystal X-ray diffraction. It is a well developed technique. And I'm going to give you some examples. And the first types of structures I would like to describe are zeolite structures. How can we discover novel zeolite structures and then use these structures to see what kind of properties they will have? And the zeolite structures is actually based on silicon dioxide. So it's very simple composition, and you can have silicon tetrahedral, and they are corner shells, and they are built in a framework. For example, here you can have different descriptions, and normally we're using PT atoms, so it's a silicon-silicon connection because all the silicons are full coordinated. And it forms certain ring sites that is generate a pore. This type of pore is like about 6 angstrom, and this typical like molecules can diffuse in and out, and it can act as a catalyst or absorbent. And each zeolite built many different building units. For example, this one can generate many different types of zeolites, and so that they are basically with a very simple building unit, silicon, tetrahedral, and you can build a lot of zeolites. Actually, if you make like modeling calculations, there are more than several millions of zeolite types, possible zeolites. But in reality, actually, there are only 253 zeolite framework types so far discovered, and like 40 of them are natural minerals. And it's still very, very difficult to discover new zeolites. The reason was actually because many of the zeolites crystallize in various tiny powders and difficult with single crystal X diffraction. I just give you an example, like there are 28 new zeolite frameworks discovered since 2015. Only 3 of them were determined by single crystal X-ray diffraction, and 5 of them by X-ray powder diffraction, and all of the rest were discovered by electron crystallography, 20 of them. So this shows that the power of electron crystallography for really working, studying the structures of zeolites. Many of them were discovered before, but their structure could not be solved because of the limitation of the existing techniques. And this was the first zeolite structure we determined using rotation electron diffraction. And it's an aluminum phosphate. As you see here, this is the data we show. And it contains large rings. We usually count this ring size. This is the 16 polyhedral, so called the 16-membered ring. And the structure was solved basically from electron diffraction. And this is another example. This is SM43. These names were named by the people who developed this material. This one was discovered already, patented in the 1980s, but the structure could not be solved until recently, 2017, and using electron diffraction techniques. And so this shows that how important it is to have good good technique in order to discover new materials. This one has a very good CO2 absorption capability, so it's good for CO2 separation. There is another type of zeolite, and this is another zeolite also developed by ExxonMobil, and it was also discovered 1981, like 30 years ago. And the structure could only be solved in 2015. And because now we're able to collect electron diffraction data in 3D, as you see here. And the structure is very complicated. And by discovery of this material, we find out some common principles and between the different materials, and we could actually discover a series of new zeolites that have similar properties. If you look at different colors of these building units, actually they correspond to different cages, and they are built in the exact same building unit of all these zeolites. And we discovered a series of zeolites, and you can see here also they have shown that this zeolite have very, very good CO2 uptake properties. The reason is that the ring size of this zeolite is exactly similar to the CO2 and the nitrogen, and so that the nitrogen is too large to enter, but the CO2 is perfectly to enter, so that you have very fast and very high CO2 uptake, but exclude nitrogen gas and also methane in this case. So, and it also can be cycled many times, very, very stable. So this is a very promising CO2 absorbance. And we have also studied other types of materials. This is a layered cationable aluminum oxyhydrate. And this, most of the zeolite are ionic, so that it has negatively charged. And this one has positively charged, which means it can absorb anions with negatively charged heavy, for example, heavy metal anions. And this was the structure, so determined also by electron diffraction. And you see it's a layered structure, and here it's chloride is between these layers, but this chloride can be exchanged with other anions, like for example the chromium. So if you use this one, and you see that very high uptake of this anions, so that makes it possible to really absorb a lot of heavy metals from very low concentration of the solution. So this is also important. Now I move back to another type of materials, that is metaorganic frameworks. And the metaorganic framework is built by metal clusters and also organic linkers. And it has a very unique property because it can be tunable. As you see here, if you just use the same inorganic clusters, but choose different organic linkers, and you can change the pore size. This red, yellow sphere shows the pore, and also to functionalize the linkers, and so that you can really make a large range of different porous materials based on exactly the same principle. For example, this has the same topology. We call this iso-reticular metaorganic frameworks because they have the same topology. And many of these framework materials were solved by single crystal X-ray diffraction, but now when people start to get larger porous materials, and it's more difficult to get single crystals. And we have developed a series of iso-reticular lanthanide molds. So it's based on the same lanthanide chains. So it's a lanthanide metal, but with different linkers. As you see here, they're all look like a triangle, but different sizes, different. And so when you have larger and larger linkers, the pores becomes larger and larger, which means you can tune the pores. And because this lanthanide you can use different elements, and you can get different properties. And for example, you can tune the luminescence property just by doping different lanthanide elements. For example, here you can dope, and then you can make use of the pores and to insert a different gas molecules to change the luminescence properties. So by these two different things, you can really change the color of the absorption of the mold in a different wavelength range. And you can also play with the metal clusters. In this case, you have mixed metal clusters, titanium, zirconium, and this actually the data was collected with only very short time, only 17 seconds, and from a 500 nanometer sized crystal. And this is enough to get their structure. And the structure was built by a cluster and this cluster contains both zirconium and titanium, like this kind of cluster. And the organic linker is like this here, and you can also tune the organic linkers. And by tuning the organic linkers, like if you insert the amino groups, and so you can tune the absorption. And as you see here, this the native morph doesn't have any absorption of the for light range, and but with doped with the amino groups in the ligand, with mixed ligand, you can change the absorption range, and also like change the bound gap. And in this case, you can make a different photocatalytic properties to tune the properties, and by combining different linkers, for example, like this, and finally you can use it for what, like a hydrogen evolution catalyst, which means the linker absorb the sunlight, and then they transfer it through the cluster into the platinum, and finally you get the hydrogen from it. And you can also, like another example is the tune the metal clusters also, and this is like a titanium cluster. So you can have combine the titanium cobalt cluster and the titanium cluster into one morph. It's called the MIO 100. And by doing this, and you can really tune also. This is a very complicated structure, so you can see there have cages, pores like 29 Armstrong and 25 Armstrong, two different types of cages. And but doing this, and you can we can tune the photochemical properties. So this like hydrogen production very much better comparing with the untuned one, and also even better than the normal photocatalytic, the P25. And so it also can be recycled. And we can also introduce the catalyst, for example, the porphyrin into the morphs, as like using the porphyrin as part of the linker, that's the building unit. In this case, we combine the zirconium chains with the porphyrin, and to build such a morph. And this morph has a very defined distances between the porphyrins. And so this is the distance, the spacing that is tuned based on the chains. And because of this, and we were able to tune the catalytic properties. And here you can use different metals in the porphyrin. And so this can be used for example, to make a zinc ion battery, as you see here. And you have the zinc as anode and the L as a cathode. And so you make a zinc, it has a very good recycling, and it has a very high peak power density, 133 millivolts per square centimeters. And it is much better than the platinum one. I mean, this is just a transition metal, so we can get rid of the platinum in this case. And I just want to show you a movie. I can show this is driven by the rechargeable batteries of the car, so that works. And yeah, you can have morphs like with water harvesting. This is another morph, the aluminum morph, also based on the chain. It has a very high surface area. And if you look at this one has a very high water uptake capacity, as you see here. So with just a slightly different temperature, that you can have immediately uptake of water. This temperature can be tuned. And so by using this one, it has a very high heat of absorption. And so this can be used actually with ultra low temperature driven cooling and through by water absorption. And it can be recycled 500 times, 5,000 times, sorry. So this is also can be a very interesting material for sustainable chemistry. And sometimes we would like to have large porous materials, and then the structure determination becomes even more challenging because now the crystals will be even more difficult to crystallize as a larger crystals. And this is a structure like, as you see, the pore size is more than 2.2 nanometers. So this we call it mesoporous materials. And this can be also like tuned to make thin 2D materials, and that will be used for making different devices. And look at this structure determination today by 3D electron diffraction. And actually, they are very robust because it's a new technique. And we have checked, like, for example, in this case, you determine the structure from 8 different data sets collected from 8 different crystals. And each of them give the same results, as you can see here. And they are all, these are the 8 structure model overlapped. We can not only see the framework atoms, we can also see very clearly the solvents. So this is the solvent molecule, dark here. And also these are the water molecules that form hydrogen bonds. So we can really see a very good details, and the structure is quite accurate. And how accurate it is depends on the resolution. So in this case, we combine a structure, deep structure, metaorganic frame with single crystal diffraction model, and it has like accuracy 0.07 to 6 angstrom. And if we combine it with the powder X-ray diffraction, and it's 0.03 angstrom in average distance, so they are quite reliable, even we use electron diffraction data. This means that electron diffraction now can be a very good method for structure determination in the same way as X-ray diffraction. And this is the different sample materials we developed and determined using electron diffraction data. And it's not only theorized Metaorganic Frameworks. You can actually use this method to study any different types of crystals, including proteins and pharmaceutics. And this technique has been very robust, as you see, but we would like to make it high throughput to make it easier for people to use and easier to collect the data. So this is like first development is automated data collection, as you shown here. And you can actually collect the data. We call it zero electron diffraction. And in this case, the software is called Instamatic, and it's to search different grades and find different particles. And each particle, we collect one diffraction pattern. And as you see, the diffraction pattern is not as beautiful as we saw before, depends on how you find the particles. But using this technique, we can use machine learning and the convoluted neural network to decide what is a bad, good diffraction pattern, what is good diffraction pattern, and so assign a score. And so, which means we can only need to look at the small good diffraction patterns. And this can be, data collection is done, can be thousands of diffraction patterns can be collected in an hour. And with this technique, it is now possible to find not only the phases we wanted and use them for the structure determination, but we also can find the impurities in the crystal, which you cannot cannot be observed using powder X-ray diffraction, for example. In this case, we find like out of 1,200 electron diffraction patterns, we found 6 diffraction patterns that are different with the main phase. And from this one, actually, you can find, you can collect electron diffraction data and find out what this phase corresponding to. And using this technique, we could detect many new materials that were not was not seen by X-ray powder diffraction. So this is a very good, unique application. And next step, that is, we want to collect 3D electron diffraction data using automated data collection. So this was done like by, as you see here, the automated data collection is done, and we'll look at the trace the crystals to make sure that it is still selected in the electron beam. And when the data is collected, actually we're doing the data conversion and data processing immediately, so that we'll get the answer what kind of materials and what kind of crystal structures this particle can have, and so that we get immediately the answer. And when you have many data sets, and now we will not be able to look at each individual data set anymore, and we process the data, and we try to use hierarchical cluster analysis to find out what are the phases, if they are mixed phase, for example. So this is very good for identifying new phases, phase identification. So in this case, based on unit cell parameters obtained, we can find, okay, actually there are 2 clusters of unit cells, and actually they are corresponding to 2 different crystals, zeolites here. And look at each cluster, you can see, oh, and we can look at the intensities obtained from the diffraction spot, and also to make a further clustering and to find out which of the data sets are closely related to each other. Then we can merge this data and solve the structure using combined data. And this can be used for so many new structures. So important to know the data now is collected in an automated way. The current evolution of electron diffraction techniques has been very fast. First, it was taken like an hour for data collection. Now it takes less than 1 minute for data collection. You can collect the automated electron diffraction data. It's even faster, about 1 minute per data set. And you can also collect many particles per hour, so that very fast data collection in order to be able to identify what kind of crystalline materials you have in the sample. So all this automated data collection and the data processing pipeline are being developed, and we are still optimizing them. So I hope that later this will be very important for people to be used for discovering new porous materials, and be able to explore their functions. And in the last few minutes, I wanted to move to a different topic. That is, when you work with zeolites, usually it is very difficult to get large pore materials because of the building units is very small. It's only silicon tetrahedral. And sometimes we need to introduce extra pore in larger pores in order to improve the diffusion of the molecules and to improve the performance of the materials. And we can also introduce like catalysts into the pores. This is an example. For example, palladium Nano Catalyst is inside the Metaorganic Frameworks. What we do is that we put a precursor of like a palladium precursor, palladium chloride, for example, implemented in the Metaorganic framework that is functionalized by the amine group on the linker. And then reduce it. And so in this case, we hope that the nanoparticles will be inside the mold. How do we know that? And actually, we can use electron tomography. And this is a technique, 3D technique. You tilt the crystal, like takes the images, that's what you showed here. And then by combining it, and in the computer, actually you can see here, you can cut through the 3D. So one layer and the layer, and on the image in the right, you can see the different layers. Now I'm cutting through these particles, just to look at every thin layers. And you see here now that actually the particles are mostly small particles are inside the pores, and the larger particles are outside the particles. You can see it here. So these are the larger particles, and now you see that the larger particles are on the edge, and the inside this one it's smaller nanoparticles. So this is what really we want, and this catalyst it turned out to be very, very useful for a lot of different organic catalytic reactions. And my collaborator, Billy and Martin Matuta's group have been exploring this in a lot. And we can also improve the transport properties by actually find zeolite catalyst instead of making nanopores inside this the zeolite crystals, and we make like this kind of structure sort of find just on the surface of the crystal, and by tuning the ratio of these finds and with this particle sizes, and it is possible to tune the properties. So this is how the tomography shown you. And on the surface, you know that this particle looks like a single crystal by electron diffraction, but how it looks like inside, it's not possible to see. Only by electron tomography, you can see that, okay, really it is a fine zeolite. And this one is also very useful by changing from this typical zeolite into this fine zeolites, and you can get much, much higher performance for the catalysis. And so tuning the pores, and it's important, and of course you use electron microscopy to know that how the pore structure looks like is also important. And the last example I want to show was to introduce really pores into the inside the zeolites. This is also a zeolite Y that is industrially used for cracking of large molecules into smaller ones. For example, to roll crude oil into petrol we use today. And but there is always a problem with the molecular diffusion and how to introduce the transport and the molecular highway, we call it inside the channel. And my collaborators, Javier Garcia Martinez, they have developed a surfactant templated post-synthetic method, and to introduce mesopores into the commercial zeolites. And you can see that beside this normal pore, this pore is about 1 nanometer. That is the intrinsic pore of the zeolite Y, and introduce a well-defined pore size about 4 to 5 nanometers, and inside the zeolite. But it is very difficult to visualize how the pores look like if you just use images like this. And this introducing these pores actually increase the performance of the cracking and by like 4%. And this is a huge benefit for making like to increase the productivity and of the catalysis. And how do we know how the pores looks like? And we performed both electron diffraction 3D data, as you see in the left, and also the tomography on the right. And by looking at these two, combining these two, actually we are able to see the combined. You have crystals. Actually, you can see that this crystal has two different lattices, the red and the blue, green, and they are twins, so they are different domains. And also, like look at the morphology of that, and by combining all these things, you can see how the molecular way, highway looks like inside the zeolite particles. And this is the 3D perpendicular cutting slides. As you show here, the white spots are the mesopores, but if you go a little bit closer to these mesopores, you see that they are very, very empty inside, and which means that a molecule, like from one side, and can really go through this zeolite particles and really can get like get to the catalytic side and finally to make reactions, and finally the product will be diffused outside to the other side and exit the particles. And so using this technique, we were able to really find out how the connectivity of the pores. Oh, sorry, I have shared the stop. And this is actually, I have just the last slide. It's strange. Sorry. I don't know what happened. Seems like I closed my
Thomas, do you have any idea?
so yes, I know that I just need to find my slide, and I actually have just the last slide to show, but I don't see that in my screen. That's the problem. I need to share the screen, but I don't know where to share. I do this instead, sorry. Sorry for the problem. I shared the screen. Which screen do you see?
Xiaodong, maybe if you share the screen, probably that might be easier.
I shared the screen, but now I stopped sharing. I share it again.
Yeah.
Yes, I will share the screen. Yes.
Yeah, we can see it. We can see.
What can you see? Can you see the wrong screen, right?
We can see the screen, but it's divided. So there is yes. If you click that, yeah.
Is that better now?
Yeah, now we can.
Perfect.
See.
Okay, sorry. So that this is a summary of the applications of using electron crystallography and electron tomography techniques, and we can use it for discovering new materials. And if you don't know the materials, and we can determine the unit cell and the space group. In this way, we are able to make phase identification of the materials. If the material is unknown, and we are able to solve the structure. And also we can use this electron diffraction to determine the orientation relationship of the integral crystals and also the crystal surface and index them. And also we can study defects and hierarchical porous materials. And so I have just talked about the image diffraction part. Of course, this method can be also used for chemical analysis. You have elemental analysis by electron energy dispersive spectroscopy, and you can also use EELs to study the chemical composition. And I hope like later some of my colleagues can mention that for that. But 3D electron diffraction really can now become more and more powerful. So which means that current standard electron microscopy can be used for work as a single crystal diffractometer, and also like to be studying many different examples today that need synchrotron radiation source. Now we are able to use electron microscopy to study that. And the last example, and I want to show that to thank my group members, co-workers, as you see here, we are now in the Corona time. And so that we have Zoom meetings also. And the people who have developed these techniques are shown here. So from Sven Müller all the way to Bing Wang, and developed a lot of technique, and we have already mentioned many students in different PowerPoints. And also many of the samples were from our collaborators, which given different challenging problems, so that makes us busy to study the further develop the method. And I would like to thank all of them. And finally, I would like to thank you for your attention.
Thank you very much for this very impressive insight into the world of electron diffraction and tomography. And I think you all convinced us that, that this is a very powerful technique, and about the progress which has been made recently. So I'm really impressed. So now the talk is open for discussion. So I encourage all the participants to post the questions in the Q&A or in the chat. Either way works. If there is no question initially, then I maybe start with one. So this is a question from a person active in catalysis. So I was interested or impressed by the example or the little battery you've shown with the electrochemical example where Metaorganic Framework was used as a catalyst for oxygen reduction. Do you have any idea on the active center, or I think it was slide 25, yeah, on the active center, yeah, or the mechanism?
Yeah, let's go to 25. This one.
Yes.
Yes. Actually, we go back one side, and we have the porphyrin, and so we found out that by this space between the porphyrins has been very important to on the like the charge transfer and the band to the band gap, and so this by tuning these ones, and we will be able to have the performance as you see here. I want to. Yeah, so we have done some calculations, DFT calculations, also to really see how to change the tune the band gap.
All right, so I assume that this was applied to a conductive material with the binder, yeah, or was that done with the binder, or just?
Yes, yeah, we have it. Yes, we have to have boundary. I need to. Yeah, so that is needed. Don't remember what boundary. I think it's carbon. Yeah, to make the battery itself.
Thank you very much. So,
yeah, Robert.
Xiaobing, yeah, please.
Xiaodong, thank you very much for a very inspiring lecture. I have a couple of questions. So the first question is, you have developed a very nice technique combining with TEM and X-ray diffraction, making the all view 360 view, which is fantastic, very inspiring. My question is, can you also use that technique for the in situ reaction? For say how the phase is changing inside the reaction? Is it possible?
Actually, yes, it is possible. That is what we are trying to do next. And currently, we made it possible just by freeze the reactions in different time interval, and to use the cryo technique to stop the reaction and be able to visualize it in the microscope.
Okay.
And we hope that in the future that we were able to use liquid cell. Actually, there are liquid cells that can make electrochemical reactions, and many of them are being using images. And I would like to combine images and diffraction to be able to really understand the structural change, not only the morphology change. And so, but there are still challenges that the current cells usually are really too large, too thick. So this is a problem. And also there are lots of electron-induced artifacts for radialysis, for example. And I think it will be possible in the future.
And while doing that, do you see any change in the phase of the material?
Yes, we do. Actually, we use it to study the structure change and also crystal growth by, for example, a structure change from one polymorph to another polymorph, and also being able to follow the change and to understand the crystallization mechanism.
Okay. Okay.
Right. So there's a question from the audience, which I simply read. So Vuduk Hafan is asking or saying, thanks for the fascinating talk. And he says, to the best of my knowledge, MOFs are quite sensitive to the electron beam. So how can we avoid material decomposition while doing electron diffraction? Thanks.
Yeah, this is a very good question. Thank you. And yes, that is really a problem. So at the beginning, we were not able at all to study metaorganic frameworks because of the beam radiation. And the techniques have been improved. As you see here, the data collection time is dramatically reduced. Now it's like about less than a minute. And we are using very, very low dose. The key is that electron diffraction requires much, much lower electron dose comparing with imaging. And so that being able to use faster data collection of electron diffraction, and this is now possible. And most of the MOFs, not all MOFs, can be studied using electron diffraction now.
Thank you. So if there's no further question, maybe I have a last one. So you've shown in the beginning this graph where which basically said that still most of the structural analyses are solid state materials are done by X-ray diffraction. And I just assume that this is maybe also due to the initial investment for the device. And I would be interested now to hear from an expert. So in which category are we when we compare in terms of price a TEM or electron diffraction device with a classical X-ray analysis?
Yeah. Electron microscopy microscopes are usually much more expensive comparing with standard diffractometers, in-house diffractometer. And the main reason why electron diffraction, electron crystallography were not widely used was of the fear of dynamical scattering, because electrons interact much strongly with metal, and it gives multiple scattering. So the electrons are not scattered only once, like X-ray. And at the beginning, and people believe that they are not very useful for structure determination. And actually, it was even in the textbook of physical chemistry of Atkins that you could not use electron diffraction. And by being able to collect 3D electron diffraction data, and we are really making unconventional data collection. And it seems that the dynamical effect was reduced. And at least now we have intensity. It was really, as I showed many examples, it was possible to get accurate structures based on electron diffraction data. Now, I hope things will be changed, and so many companies are now getting involved in electron diffraction. One of them is Ricardo, that is typical diffractometer companies. Now they are working with electron microscopy company and trying to build something. And now I think in the future, you will be cheaper diffractometer by electrons, probably in the same range, a little bit higher than normal diffractometer. So if we will show that there is a need and there are a lot of interest, certainly the company will make a product.
Thank you very much. I guess that also in the interest of time and our schedule, I would like to hand over to Xiaobik. But before Xiaobik, you start, I would like to thank our speaker, Xiaodong, once more for the very nice and interesting talk. Thank you very much.
Thank you.
Yeah. I will stop sharing.
Yeah, thank you. So thank you, Xiaodong, for this very inspiring chemistry. Thank Robert for being the chair. So now we move towards the homogeneous catalysis, and it's my great pleasure to introduce my very good friend, Aryan Clay, as a speaker today. So quite normal that we start with a brief introduction of our speaker. Most of the information actually it's in my mind. So still I ask Aryan to send me his CV just to, just to repeat all the things, just to repeat my memory. So Aryan received his PhD in 2000 from the University of Utrecht in Netherlands, from the group of Professor Gerard van Coten. In 2000, he moved to the industry first at Avantium, and later he came back to academia to join the group of Professor Javier de Mendoza in Madrid as a postdoctoral fellow. He continued his postdoctoral research with Professor Just Riek at the University of Amsterdam later after Madrid period. In 2006, he was offered a position as a group leader at ICIQ and later was promoted to ICRIA professor in 2011. Sorry, probably, Aryan, I probably misspelled or my Indian accent, I have mixed it up. There is no doubt that Aryan has won plenty of awards, so I'm just trying to mention some of the very important things. So very recently, he has received that RSEQ Scientific Excellence Award from the Spanish Chemical Society. He joined Organic Chemistry Frontiers as an associate editor in 2019. He holds a visiting professorship in Dalian University in China, and he has also invited lectureship at Tokyo University in 2021, but I guess has been postponed due to COVID. He was recently named as a fellow of the Royal Society of Chemistry, quite prestigious, and he is also in the advisory board of many journals, many prestigious journals such as Chem, Journal of CO2 Utilizations, Molecules, and Current Organic Chemistry. Sorry, one more addition, there would be ChemCat since 2021. He has co-authored around 200 international publications, and he has 4 patents. So with all this information, Aryan, we are very much looking forward to hear inspiring CO2-based chemistry. So stage is yours, Aryan.
Thank you very much. I hope that I can surpass your introduction, yeah, which has been very nice. So thanks to that. Also, I'd like to thank all the organizers, of course, of this lecture series. I've been enjoying these lectures quite a lot. So including Shupik, Robert, and Adam, and all the others that have been involved in the, let's say, organization of these lectures. Okay, let me share my screen. Right. So hopefully you can all see now my screen. Today I'm going to talk about a topic that has to do with carbon management in general. And of course, the context in which we would like to present this work is basically sustainability. We all do know that sustainability is a way to make sure that the future generations that will follow us will still have access to, let's say, clean energy, fresh water, and other things that we seem to take for granted. I've depicted here a number of topics that I think are really, really important nowadays. So we zoom in a little bit. Here we have global warming. Hold on, I'm going to right, I have it here. Okay, so as we all know, global warming is really important, a problem that we are facing nowadays with a lot of, let's say, negative consequences. And this is obviously connected to the, let's say, carbon cycle. So the carbon cycle is something that is typically controlled by nature. However, due to humans and their activities, and especially related to fossil fuel burnings, we are now facing an offset of this carbon cycle. And so we have to make an effort to get into, let's say, a better control of this cycle in order to sustainabilize our world. A little bit connected to this is plastic pollution. I think we all know that that is one of the major problems nowadays in our societies, and especially when we focus on the occurrence of microplastics. So this is considered to be one of the major problems connected to plastic pollution. And this picture basically shows that plastic gets everywhere. So for some of you that are not aware of the term, but plastic soup is generally referred to as let's say, seas and oceans being contaminated with plastic waste. Of course, food waste, we throw away a lot of food, and I didn't know, but I came across this picture, which I think is very nice, because it shows that about 10% of the greenhouse gas emissions nowadays come from food waste. So this is an enormous amount, of course. Obviously, also in agriculture, there are sustainability problems, with a little bit less or more related to let's say, controlling the carbon cycle, but also related to resource issues. If we think about the energy needed to grow crops that we need to feed basically the world, this is of course a particular issue when we are dealing with a increase of the global population, and other things like climate change is also putting a, let's say, a burden on having a sustainable agriculture. However, if we consider a number of these problems, and particularly waste that we produce through chemical processing or through other processes that are non-natural, also including the natural ones, we can make use of the waste. And of course, then in that respect, circular economy is a concept that has recently gained a lot of importance. So that means that you would have to find technologies to reuse the waste that we produce, and in that way we can basically have a completely closed loop of our, let's say, atoms that we use for chemical production. So recycling of that waste, obviously, into products that have added value is of economic importance. So this is something that we have to make sure that we can connect to with our chemistry. And if we want to stick a little bit to the, let's say, the topic of sustainable plastics, the use of renewables is currently now gaining importance, and especially if those renewables are bio-based. However, also the plastics that are not bio-based, it would be an ideal case if they have potential for recycling or upcycling. Biodegradation would be fantastic to have. That's nowadays becoming more and more important, especially to those systems that, or those polymers and plastics that have a larger content of a bio-based component. We see in this respect, catalysis as a key enabling technology. So for those that are familiar with European project submissions and executions, this is typically referred to as a CAT. And catalysis is, of course, extremely important to make this all happen. If we want to stay a little bit in the area of, let's say, carbon dioxide recycling, this is one of the things that we consider to be one of most interesting to start with. In the case of catalytic carbon dioxide recycling, there are a number of categories of products that you can think about. So the first category is reductive coupling reactions. That means that the carbon dioxide is being reduced by electrons and protons, depending a little bit on what the other reaction partners that you have. But you can make products typically, being formamides or alkyl amines, lactones, and carboxylates. And the oxidation center of the carbon that was originally present in the carbon dioxide changes from +4 to a maximum of -4. The second category is basically energy storage. So for those that work in the field, solar fuels is the other term that you will see or come across the open literature. And basically what happens is that you store the energy, you take CO2 as an energy carrier and you reduce it to formic acid, methanol, or even methane. And also in those cases, the oxidation state changes from +4 to +2, -2, and -4 respectively within the series that is shown over here. However, in this case, reversibility is key. So you would have to take the energy out at some point in time. So you can store it, that is nice, but you would have to take the energy out once you need that. So reversibility is a key concept in this category of carbon dioxide conversion. And my group has been very much interested and also active in the area of non-reductive couplings, where we take carbon dioxide and we do not change its oxidation state, but we combine it with what we call higher energy co-reactants like epoxides or other cyclic ethers. And in that way, we can have a thermodynamic driving force. And with the help of catalysis, we can make then the reactions kinetically feasible. And the typical products that you can think about are cyclic, linear, and polycarbonates, and related compounds like carbonates and ureas. And you will see a number of examples where we have used those compounds as targets in catalytic upgrading of CO2. So this is essentially what we have been doing over the years. So if we take here our CO2 molecule, we use catalysis in order to make heterocyclic compounds. So these are the compounds that we have been focusing on for quite some years, using mostly sustainable metal catalysis and organocatalysis, so a little bit to stay on topic. And we have not only been producing heterocyclic compounds, but also polymers, where we can incorporate CO2. Then in a, let's say, different line of work, we are using metals, transition metals, in order to convert these heterocycles into a number of different, let's say, target compounds, including fine chemicals, pharmaceutical or intermediates, bio-based building blocks, and so on. And of course, the end-of-life disposal of these compounds, these products, or their decomposition will release, again, CO2, which then, of course, in an ideal case, we can recycle back into heterocycles and polymers. So that would be, let's say, our way of thinking about a circular chemistry. Why are we interested in organic carbonates? Well, there are several reasons. Because they have a lot of application potential. A lot of people don't realize that lithium-ion batteries that power, let's say, phones and laptops, they always have an electrolyte being involved, of course, and those electrolyte solvents can also be represented by certain organic carbonates. So that's why one of these applications, being electrolyte solvents, is quite important and also large-scale application. Isocyanate-free polyurethanes, so you see these foamy materials, polyurethanes, large application area of plastics. And there is now a lot of activity in replacing, let's say, some of the harmful chemicals that one needs to use in making the polyurethanes, so these are isocyanates, to replace them by organic carbonates, and in that way making isocyanate-free or low polyurethanes, and that would imply a more sustainable alternative for the present polyurethanes that are being, let's say, or that are commercial. Biodegradable materials, I'm not going to go too much into that, and drug molecules. So this is Proto. I will show you also in this lecture how you can make more complex molecules out of CO2 and out of, let's say, the heterocycles that we have made over the years. Our inspiration in terms of synthetic application comes from nature, as for many synthetic groups. These are just 4 examples of rather complex cyclic carbonates. So in most cases, we are dealing here with a 5-membered ring cyclic carbonate. However, the rings can also be larger. So here's an example of a 14-membered ring cyclic carbonate. But more importantly, as you can see, the substitution degree and also the functionality of these molecules is actually quite elevated. So the question that arose many years ago in my group was, can we mimic the complexity of these compounds, and how would we devise, let's say, catalytic processes that will allow us to access these kind of, let's say, complex molecules? So we started with that idea, but first I'd like to explain a little bit mechanistically, very shortly, how the valorization of CO2 in the presence of cyclic ether, let's say, substrates work. Typically, you have a Lewis acidic complex that activates an epoxide for nucleophilic ring opening, as you see over here. So you will make this first intermediate. This is what we call a metal alkoxide, and that metal alkoxide, if you control the reactivity well enough, reacts with CO2. So we basically get an insertion in this metal oxo bond, let's say, bond, and we form here a metal carbonate. And this carbonate can now backbite onto this carbon center, forming here the cyclic carbonate. So that is in the case that you are focusing on a heterocyclic product, the desired pathway. Obviously, there are parasitic pathways. So here, this metal alkoxide can evolve into a polyether by repetitive, let's say, epoxide insertion reactions. And of course, you can also have alternating epoxide and CO2 insertion reactions to form a polycarbonate. Anything that goes in between is also possible, but I'm not discussing that in great detail over here. So the challenges that at the time that we entered the field were plural. That was to create functional products and also highly substituted products. And the reason for that I will come back to in a minute. Larger ring heterocycles, so the ones that are 5-membered are relatively easy to make, but how would you devise methods to make 6, 7, 8-membered cyclic carbonates or related molecules? And also the low reactivity of oxytanes and highly substituted epoxides at the time was very difficult. So with these challenges in mind, we started to develop our chemistry. And I'd just like to recall the very simple, let's say, schema over here, where we have an alkene that, of course, can be easily converted into an epoxide, and then an epoxide together with CO2 is the perfect combination and probably the most, let's say, utilized method for making a cyclic carbonate. So these are just 3 examples of our former work where we developed very, I would say, powerful catalysts for making slightly more complex carbonates with sterically demanding groups, as you see over here. So this is just one example. So at the time, that was, I think, a nice step forward. This is a reminiscent molecule where we wanted to control the stereochemistry that you see over here. So this is a cis stereochemistry, and by proper hydrolysis, you can get then access to cis diols, which are interesting symptoms from a pharmaceutical point of view. At a later stage, we also developed terpene-based cyclic carbonates. So these are more substituted, as you can see. So now we're getting somewhere with functionality and substitution degree, and in terms of mimicking what we see in natural compounds. And well, I think at that time, this was sort of the limit where we could reach with our, let's say, initial catalytic processes. There are other uses of carbonates. So carbonates are not just useful for biomedical applications or for use as electrolytes, but you can also use them as synthetic intermediates. And one of the, let's say, symptoms that we have used over the years, over the last 5 years or so, are these vinyl carbonates. So these are carbonates with vinyl substituents, which under appropriate conditions you can activate. And by doing so, for instance, in the case of a palladium catalyst, you can then do alytic substitution reactions. And those alytic substitution reactions are sometimes quite difficult and elusive. For instance, in the case where you want to design methods for making olefins that are basically tetrasubstituted, and you want to control at the same time the stereochemistry. So that is something that we have done over the years. We have varied that also towards alytic sulfones, and also these 1,4, let's say, unsaturated butene diols. In 2018, we reported on this, what we call an Umpolung type of process, where we take one carbonate molecule that we convert into a nucleophile, and it reacts with an electrophilic counterpart to do a formal cross-coupling reaction. As you can see, this is now becoming quite a difficult and complex molecule, where we have here a quaternary carbon center that is highly functionalized with an aldehyde, a substituted aryl vinyl group, and a lytic group. So there are, I think, no methods out there that can make this compound in one step, and our method basically made that happen. So we recently also reported on an asymmetric version of that process, which was highly, highly challenging, but I don't have any time to go into it. So I'd like to move on. Same thing here with vinyl carbonates. You can make them useful for asymmetric conversions. So here we are basically doing similar type of chemistry, but then we are controlling the regional selectivity in these alytic substitutions in a different way, and in the presence of a chiral ligand, and then we can make chiral alytic amines, as you can see here, different types, or chiral alytic sulfones, which are particularly attractive for, let's say, drug development programs. And we have also been increasingly interested in knowing how these reactions proceed. So to know about the details and what is controlling the regional selectivity, the stereoselectivity, and the asymmetric induction. And this is, of course, very, very useful if you want to use this knowledge for devising new types of transformations. There are other options. You can also use alkyne-based carbonates. So this is just another example where you can make propergylic compounds, as you see over here. So this is a propergylic sulfone. Here we have dienes that are stereoselectively made, where we can borylate or diborylate very selectively, regioselectively, and stereoselectively. And also a recent example is shown over here, where we have made alene compounds, or basically silylated allenes, also in a, let's say, very chemoselective fashion. Of course, there are also more simple type of operations. So carbonate, as you see over here, can be ring opened by alkylamines. Aryamines, at the time that we started to investigate this, was still relatively unexplored and relatively impossible. But we found that by using an organocatalyst, this TBD molecule, this heterocycle, we can make this reaction happening at room temperature. And in this way, you can make carbonates, and these carbonates are potentially useful as intermediates. Second example, reported by the group of Détrembleur in Belgium, they made use of these exocyclic, let's say, olefin-based cyclic carbonates. And these are rather reactive molecules that in the presence of this thiol will ring open at this position. So you would form here a thiocarbonate linkage, and in that way you can grow the molecule into a formal polythiocarbonate. So this is a very nice example of using ring opening chemistry and retaining all the atoms of the, let's say, the cyclic carbonate substrate, and to create new polymer architectures. More recently, that I will just indicate it very, very briefly, we have seen that if we take a cyclic carbonate in the presence of cyanide, so this is essentially a carbon-based nucleophile, we can get attack onto this position, and then we get a rather unusual CO2 extrusion and also the extrusion of acetonitrile, forming first a Michael acceptor or maybe I should say an unsaturated ketone, which then in the presence of cyanide does a micro-addition reaction, and then you can get these beta-cyanoketone products. And this is another example of how to use ring opening chemistry based on cyclic carbonates. Okay, so far I've been discussing cyclic carbonates and their use in well, the formation of various kinds of let's say fine chemical intermediates and other types of molecules. However, at the same time, we were wondering if we could devise new methods of making cyclic carbonates to be able to control and modulate the sterics and electronics of the cyclic carbonate ring substituents, but at the same time also to have a way to introduce more substituents than the typical ones that are shown in literature. So if we consider the classical mechanism, and I'm just showing here one example, so this is the example based on epoxyamines, but it's similar true for epoxy alcohols. If you have classical mechanism, then Lewis acid metal will activate that epoxide for nucleophilic ring opening, as you see over here. And then, of course, we get a series or a sequence of steps that will then form the epoxide and CO2 in this cyclic carbonate. The important thing to note here is that we have the functional group still residing at the outside or of the, let's say, cyclic carbonate ring. And we thought about using this kind of functionality in what we call a substrate-driven type of concept. So here it is shown in the presence of CO2 and an effective Lewis acid and Lewis base, we can basically form intermediate species. So these are essentially hemiesters of carbonic acid or carbamatic acid. And in this way, we basically form a nucleophilic species in situ, which would then attack this epoxide. So there would not be a need for an external nucleophile, which is typically a halide, to be present, because we would make it in situ. And in this way, we would provoke an intramolecular nucleophilic substitution reaction. And what we now see is that the, let's say, originally functional group that is, well, outside the, let's say, ring of the substrate is now incorporated into the new ring that we make, and we basically make a totally different product. Of course, we looked at that in more detail, and then we designed quite a general method for making these kind of what we call alternative products, which are typically more difficult to make, especially when we increase the substitution degree. And as you see over here, there's just a few examples of highly substituted carbonates, but also carbamates, as shown over here. And this molecule is actually a drug molecule commercially sold, is designated or known as toloxetone. And the interesting thing here is that when you do variation of that aromatic group that is attached to that nitrogen center, you can actually make potentially a whole series of pharmaceutically interesting intermediates. Well, how does this work? We are very much interested in how the chemistry works. Well, taking an epoxy alcohol, a very specific one, so this is a chiral one, we thought about making this product, and this was our, let's say, our hypothesis. So we would make this hemiester of a carbonic acid as an intermediate, and then we would get this, let's say, attack on the epoxide carbon over here. It would then ring open that epoxide. It would produce then this product. And this would follow then a typical 5-exotec cyclization. However, we could not determine here the absolute configuration, so this was not suitable, this product, so we had to convert it into this, this benzol protected derivative, and this was now suitable for X-ray diffraction. And finally, we were able, by X-ray diffraction, to determine the absolute configuration. And what we saw is that we see inversion of configuration at this carbon center, and that is exactly what you would expect on the basis of this mechanistic proposal. Another proof for this mechanism was delivered by this deuterated glycerol. So we have deuteration here, monodeuteration on this carbon of the glycerol. And of course, if we would follow the same mechanistic proposal, we would have to form the glycerol carbonate with the deuterium on the outside of, let's say, the cycle, the carbonate cycle. And this is exactly what we see. So we see exclusive formation of this product, and therefore this also supports very nicely the proposed mechanism. Well, we looked at that in much more detail. So we collaborated with two colleagues, Carlos Bo and Atsushi Wakawa, to not only look at this theoretically from a computational point of view, but also from the point of view of in situ analysis. So that would be operando in situ infrared or ATR IR analysis. And we know that the reaction in the presence of our aluminum complex starts with the coordination of the alcohol. So that was a little bit of a surprise, but later on we found that by X-ray analysis that we could actually support this view. And then we're getting proton transfer that is facilitated by one of the oxygen donors in the ligand of the complex, which is acting as a base. And by doing so, we're making here an interesting, I would say, species where we have water also participating in order to make this, let's say, as feasible as possible, where the epoxide is now, let's say, under attack of this carbonate, and we get here a formalizing two reaction. We could confirm that also by the, let's say, structural information that we derive from the computational analysis. And lastly, we form the product which is then still coordinated to the aluminum complex. And then by simply adding glycerol, we can do, of course, ligand exchange and create further turnover. The interesting thing is that we were able to see this intermediate. This is a key intermediate where we have that carbonate attacking that epoxide. By IR, we saw a peak at 1837, and by computation we could actually confirm that that indeed is this species. And we also know that the catalytic reaction, well, experimentally we find a barrier of 23.3, and by computation we see that this barrier is actually nicely reproducible by DFT. Okay, so I've discussed so far how to make more substituted carbonates, but how would you make now the most substituted carbonate possible? So that is a tetra-substituted carbonate. Well, we know, or we knew from the literature, that tetra-substituted epoxides, they do exist, but they basically do not react with CO2 under catalytic activation. So we had to come up with a different idea. And the idea was to use essentially pain rearrangement as a driving force for our development. And that's basically shown over here. So the pain rearrangement is nothing else than a base-mediated isomerization of this epoxy alcohol into this epoxy alcohol. And if you follow the color coding, you see exactly what I'm talking about. So we thought that we could do something similar with epoxy alcohols in the presence of CO2 and a suitable catalyst, that catalyst being mostly a basic or an N-heterocycle, doing the catalytic job. And we thought that we would be able to form this carbonic acid, deprotonated carbonic acid intermediate, making it nucleophilic enough to attack that position. And in that way, we would form this carbonate, which is essentially a di-substituted carbonate, as you can see over here, with a tertiary alcohol unit. But we found that this is isomerizing to the more substituted carbonate you see over here. And now this alcohol that we see, or that is pendant, is a primary alcohol. So the difference here is a tertiary versus a primary alcohol. And from our basic organic knowledge, we know that we can selectively trap that primary alcohol. And by doing so, we drive the equilibrium to the side of what we call the most substituted carbonate. So we thought that this would be an extremely interesting and new way of making these kind of, let's say, coupling reactions feasible. So Sergio, a PhD student at that time in my laboratory, he made this happen, and he found that by making use of DBU, which is shown over here, and acetylimidazole, which is nothing else than an acylating agent, we can form this cyclic carbonate with 3 substituents. So we start off with 3 substituents, but we also make here a cyclic carbonate with 3 substituents. And this is, of course, a sequence of steps. More importantly, this reaction is very, very, let's say, attractive in terms of the reaction conditions. So we can do this at 45 degrees, at least for the first step, and the second step can be done at room temperature. But the steps can be easily combined. and you can get good yields of these, what I would call rather elusive structures, where we can have different functionalities, let's say, present in the cyclic carbonate target molecule. So double bonds or epoxides or even two, or double bonds or epoxy groups. So Sergio took that one step further in order to make tetrasubstituted carbonates. At that time, I think we take into account CO2 epoxide coupling reactions was the first example of a more general process that allows you to do that, especially under organocatalytic control. And here you can see that we have produced a number of interesting and rather elusive type of cyclic carbonates. Well, how does it work? If we take basically this epoxy alcohol, what we do know is that there is no conversion in the presence of only DBU or CO2, which rules out, at least from our point of view, a classical pane isomerization of that epoxy alcohol and subsequent reaction with CO2. So we first make the carbonate, we get the carbonate to isomerize, and then we trap basically the most reactive one by using an acylating agent. Another piece of proof that we provided was if we isolate by column separation mixtures of that are, let's say, the non-equilibrium mixtures, then we see that they, once they are subjected to catalytic conditions, they equilibrate to the, let's say, typical 7:3 ratio that we see for a number of, let's say, a number of these transformations. As a third proof, we took basically two different starting materials, and if our hypothesis would be true, then basically it would lead to the same product, and this is exactly what we see. So we get a tri-substituted carbonate being formed from both starting materials under more or less similar conditions. Of course, in this case, this is a tertiary alcohol that needs to be activated at slightly higher temperature, that's normal, but we get essentially the same yield and the same selectivity in these reactions. So that is proof for the existence of a pre-equilibrium at the carbonate level. Well, then we thought, okay, we can use epoxy alcohols. Can we now, for instance, using homoallylic type of compounds and making the epoxy or epoxidized substrates, and can we then create larger ring carbonates? That was essentially the question. Of course, the first step is pretty standard. So we have made use of our, let's say, aluminum complex combined with a bromide or iodide, in this particular case a bromide nucleophile, and we can make these cyclic carbonates rather easily. Yeah? So we do this separately. The second step is a little bit more complex, but what we do, we use basically DBU again and acetylmidazole, and we get here a 6-membered cyclic carbonate being exclusively formed. Well, the way this works is as follows. This essentially, the 5-membered cyclic carbonate is in equilibrium with a 6-membered cyclic carbonate. However, when you take the NMR of this 5-membered cyclic carbonate, you don't see this 6-membered cyclic carbonate, let's say, being populated in your NMR tube. And that's because the equilibrium is almost on the side of the 5-membered cyclic carbonate, which is the thermodynamically more stable compound. However, we do know that this equilibrium exists because once we get to this stage, we can acylate, of course, this primary alcohol, and we can drive the equilibrium to the protected 6-membered compound. So we made use of a number of these 5-membered cyclic carbonates, and we can produce then also their respective 6-membered cyclic carbonates. And this is, I think, one of the few methods where you can go from a 5-membered to a 6-membered, let's say, ring product. So this is quite unusual. We know how it works and what is the key driving force. So if we start with a 5-membered cyclic carbonate, we make the 6-membered one, and then we protect. We see that the second step actually is more easy than the first step, and that the intermediate product is thermodynamically uphill. So that also is in line with what we see experimentally. And we do know that the reaction is thermodynamically feasible and kinetically also feasible at room temperature. If we then compare the protection of the 6-membered cyclic carbonate and the 5-membered one, so the starting material, then we see that the 5-membered one is much more, let's say, energy demanding. And this explains nicely why we basically can convert the 5-membered alcohol-free product into the protected 6-membered cyclic carbonate. So why are these compounds important? Well, these are important because you can make, let's say, polycarbonates from 6-membered cyclic carbonates by ring opening chemistry. We tried that. At that time, we were unsuccessful for reasons that I will not go into. But we decided to tackle that problem. So it's maybe not CO2 chemistry, but at least it is related to, let's say, our wish to prepare these compounds with some larger diversity. So basically, the people shown on this slide, mostly Christina and Bart, in terms of the synthesis, took these alylic alcohols, so these protected alylic alcohols, so these are nothing else than O-Bach derivatives, and under suitable photocatalytic conditions, you can basically make this benzylic radical, which you can then oxidize by a single electron oxidation, which will produce then this intermediate, and this intermediate is set up to do recyclization onto that position, so this benzylic cation, and expelling isobutylene, and in this way you would make a cyclic carbonate with different ring substituents. And these are potentially interesting for ring opening polymerization, and they have a different substitution, so we were very much interested to see what this substitution beholds and what kind of, let's say, properties we would be able to design. So we made a number of these derivatives, so these are just a number of examples, as you see over here. And of course, we were interested in their, let's say, suitability to serve as monomers for ring opening polymerization. And that is what you see over here. So what we do, we break this bond, essentially. Benzyl alcohol is here an initiator, so it's activated in the presence of a catalyst. And then what we do, we basically form here a polycarbonate, which now has in the main chain at these blue colored carbon centers substituents. And what we do see is that, well, these are basically a little bit the data that we collected so far, that the reaction is fully region selective. So we only see one type of polycarbonate being formed at room temperature. And if we do a differential scanning calorimetry, we see that the glass transition temperature of that polymer, or maybe I should say oligomer, is plus 37. And if we compare that with the literature data for the polymer that has no substituents, then we see that there is almost, almost up to more than 50 degrees of difference in the glass transition temperature. So that actually nicely shows that indeed substitution of the polymer makes sense if you want to create polycarbonates with different properties. However, if you increase the steric bulk here too much, so this is a tri-substituted cyclic carbonate, we basically saw that this is unreactive in reopening polymerization, and that makes perfect sense because in the X-ray we see that this carbon center is actually blocked from both sides for an incoming nucleophile. And so that gives also important information in how to design future monomers. As a last, let's say, example of how to use carbonates in substrate-controlled, let's say, reactions, I'd like to discuss the use of these 1,2 alkyne diols or alkyne substituted 1,2 diols. We recently developed a methodology where we can use a silver catalyst in the presence of a ligand under these conditions, forming these, let's say, cyclic carbonates with exocyclic double bonds. And by having this intramolecular nucleophile or pronucleophile being present, which can be activated under certain conditions, we can actually forge here a new oxygen or carbon-oxygen bond. And this then isomerizes basically to what we call, or what we have designated, a keto carbonate. So we have made, I think, almost 35 examples in total. And as you can see over here, we have examples of di-substitution, which are shown over here, tri-substitution, and even tetra-substituted carbonates that can be actually easily made and under rather mild reaction conditions. As a last example of, let's say, how to use this substrate-controlled activation, I'd like to show you some recent results where we took glycerol in the presence of CO2, and now with a supported catalyst that we can load, as you can see over here in the picture, in a packed back reactor, which is over here in this schematic, let's say, overview. We can do flow catalysis, yeah, so we can make glycerol carbonate, and we can make that essentially halide-free, yeah, under reasonably mild conditions, and we can make multi-gram scale synthesis of that compound under I would say, extremely stable conditions. So this is when we take samples and we look at, let's say, the overall conversion of the substrate, in almost all the cases, we see close to, let's say, 100% conversion of the substrate. Okay? So in this way, we did the reaction at 70 degrees during 48 hours with stable production of that glycerol carbonate, which gave us about 18 grams of that glycerol carbonate. And it shows very nicely that also this chemistry, substrate-induced CO2 conversion, can be translated to flow catalytic processes. So the second part, which is a smaller part, I'd like to dedicate to the formation of some polymers, polycarbonates mostly. And as you all know, in the field of polymer, let's say chemistry and engineering, there are major issues to be resolved, among which is of course the use of plastics that can be recycled and polymers that can be degraded, well, either chemically or in nature itself, in the environment, under, let's say, suitable conditions. And the reason why we started to investigate polymers was basically let's say, the problems that arose a number of years ago with BPA, bisphenol A-based polycarbonates, structures shown over here. So those polycarbonates are essentially, at least in a number of processes, made from DPC. So this is diphenyl carbonate, and then doing transesterification, you can make this polycarbonate. And this polycarbonate has very, very interesting properties, not only from a thermal point of view, but also from a mechanical point of view. And the BPA market, or BPA-based market yet, so we're only talking about bisphenol A, was estimated in 2020 to be $20 billion. So that is really, really a huge, huge market. So for us, this was an inspiration, since BPA-based products are basically, or their production at least, are being banned in a number of countries, to find a suitable alternative, a bio-based alternative that could at least partially, let's say, mimic the properties of commercial polycarbonate. And therefore, we were inspired by the rich diversity of structures that you can find in the environment or in nature, because terpenes, as you see over here, they are made from different isoprene units, so this is the key element. But you see that there is a really versatile or versatility in the structures that you can derive from isoprene and the terpenes that you can get. So this terpene limonene was essentially very attractive for us because it's one of the most abundant ones, and it's also something that you can commercially purchase at very reasonable scales. To show you a little bit that this has commercial value, this is a company that was initiated or started its activities in 2017, Peel Pioneers, and what they do, they extract the essential oils, mostly the limonene, from, let's say, waste that comes from the, let's say, juice industry, so oranges, but also lemons. They contain in their peel, so this is the part that you throw away, quite a reasonable amount of this D-limonene, and that would mean a circular solution for that kind of compound to valorize limonene into added value products. So the market size a few years ago was 250 million kilograms of waste. Yeah, that's based on weight, not based on products. So I'm not sure how many kilograms or tons of product they can get, but they found a number of interesting applications in collaboration with a number of companies. These are just three mentioned over here in terms of making fibers or nutrition additives, and also in the field of cleaning products, they find a number of applications. We thought about using the limonene, and basically it's epoxide, to make polycarbonates. And at that time, there was only one process known, reported by Jeff Coates and his group in the United States. And we developed basically a new process based on our catalyst know-how that we have built up over the years. So again, our aluminum catalyst shown over here, in the presence of a suitable nucleophile, we can make this polycarbonate. Here are basically the essential data. So it's not that we can get ultra high molecular weight. It's also not needed. I will show you in a minute why that is. But the process is quite reasonably controlled, and also the initial TGs that we got, the cross transitions, were actually quite promising. Why is this still interesting, even if you don't get high molecular weight? Well, the fact is that these kind of polymers, or maybe oligomers, so from maybe 3 to 5,000 grams per mole, are also interesting as, let's say, ingredients for resin coating and adhesive applications, where you can also make use of that double bond functionality. And this is something that we are doing right now. So these post-functional changes are very important to change, for instance, the properties, but also to cure the, let's say, polymer matrices and to get formulations that give you the desired rigidity or flexibility, if you like. And in that way, you have a lot of different possibilities. Recycling is possible, so Deconi and Xiaodong reported already on that in 2017. We independently also saw that this is actually really, really easy to depolymerize that polymer and to get back the most expensive monomer. Yeah, so CO2 is rather inexpensive, but this monomer is relatively expensive, so you better, let's say, regenerate that after the end of life use. And of course, we are looking at tech transfer, licensing, and/or valorization, let's say, possibilities, and we have some things ongoing, and hopefully I can tell you about that in the near future. Coming back to the chemistry, of course, we can make variations, so we can make use of a dummy ligand to incorporate different degrees of functionality. So we're making here a terpolymer. This is also a polycarbonate, but we can now control the amount of functionality that we have in the polymer chain from basically 0 to 100. So we can make all these variations with different molecular weights. And in that way, we can also vary the thermal properties, and we can even follow kinetically the process. So we know basically what is going on and what kind of polymer we make. Well, as I said, you can cross-link these double bonds by thioene chemistry. So this is standard chemistry, making use of a radical initiator that you can do thio addition onto that double bond. And if you then interconnect two polymer chains, you basically make the whole structure more rigid. And if you do that multiple times, you get a very, very rigid structure. So in one particular case, this case of P100, where we have 100% limonene as a incorporation, that basically means in every repeat unit we have a double bond, we can then get an increase in glass transition temperature of about 77, let's say roughly 80 degrees. So that is actually quite nice. Basically demonstrates the principle of curing or post-functionalizing these polymers. Of course, we can make use of polylimonene carbonate itself as a platform molecule. We're not the only ones that have worked in this field, but we have looked at several functionalizations using thioene chemistry, but also using other types of addition reactions, and in that way, making changes in the hydrophobic and hydrophilic nature. And I'm not going into that into too much detail. I'd like to show you, though, one particular example where we can do oxidation on the polymer. So we are oxidizing that double bond, getting here an epoxy group, which is, of course, by itself really, really interesting to consider as sort of a platform molecule, this polymer. And by incorporating a second CO2 molecule in the repeat unit, we can even make here a cyclic carbonate that also has quite modular reactivity in terms of ring opening chemistry. And so we believe that we now have made a nice series of platform molecules that we can valorize towards functional, let's say, polymer-based applications. And this is what we are doing right now. The last chemical slide, I'd like to show you one recent example of other terpene platform-based molecules. So this is beta-alamine. Beta-alamine is a compound that is produced by isobionics at several ton scale a year, but it essentially can be scaled up rather easily. And the reason why we were interested is that these are bio-based compounds, of course. So you can take sugar by fermentation technology, you can make beta-alamine, or you can take ginger root and also extract and getting access to beta-alamine. But the interesting thing is that we can control the amount of epoxy groups that we can incorporate. So we can make the monoepoxide, the bisepoxide, and even the tris epoxide, and make use of those epoxides in formation of carbonates or polycarbonates or other types of polymers. This is just one recent example that we published this year, where we are using phthalic acid anhydride, and by copolymerization we can make this polyester. And the interesting thing to note here is that we have a polyester which now in every repeat unit has two different double bonds. So we can address these double bonds individually because they have different reactivity and introduced sequentially one or two functionalities. We can also make use of the bisepoxide, and now we're getting back to carbonate chemistry. So we can make very selectively this monocarbonate that now has in the same molecule also an epoxy group and an olefinic group. And of course, this is a very interesting molecule to do divergent polymer synthesis. We can also further carboxylate it and getting access to this carbonate. This carbonate can be made multi-gram scale, so anywhere between 10 and 20 grams is not really difficult. And these are now nice precursors for non-isocyanate-based polyurethanes because we can use ring opening chemistry, making in the presence of diamines, and in that way making polyurethanes that do not necessitate the use of isocyanate reagents. Okay, so hopefully I've convinced you today that non-reductive transformations of CO2 really creates new impetus for the recycling of let's say, carbon-based species, particularly CO2, but also other carbon-based waste, or generally considered waste compounds. In the lecture today, I've shown you that terpenes are ideally suited almost in order to address that issue. And of course, the second thing that I want to highlight is that by devising new conceptual approaches, the scope of, let's say, the products that you can make from CO2, but also related compounds, has been widened to, let's say, a portfolio that now I think is suitable for let's say, getting access to actually materials that beforehand were not able to be made. I'd like to thank a number of people. So the people that are currently in the group shown over here, former members, some from abroad, some from Spain as well. We have a number of collaborations, as you can see over here. So we work with groups outside of Spain, also in Spain, and even at ICIQ, we have a number of interesting collaborations. Funding agencies and support from companies and other, let's say, organizations, they are shown over here. And the last slide I would like to dedicate to my group. So this is a pre-COVID group picture. Nowadays we have pre and post-COVID type of operations or photos. And this is, I think, also a nice picture where we had a casotala, which is something typical for the region here, where everybody's enjoying, let's say, life outside of chemistry, which I think is very, very important to have the right balance. So thanks again to the organization of this lecture series. Thank you to all the people that have stayed online, and hopefully I've shown you today that it really pays off to work in sustainable chemistry and sustainable catalysis, and I'm happy to answer any questions that you may have. Thank you very much.
Aryan, thank you very much for very nice and inspiring chemistry. It's quite obvious that I have plenty of questions, but I guess many of others have plenty of questions. So I start the question sessions. My first question is that aluminum catalyst that you have used is very nice. It's very fascinating. So I know that some of the aluminum solvent-based complexes have been used for this carbonate formation, or let's say carbamate formations. So my question is more general. What do you think, or what is your opinion for this type of catalyst for more general application in CO2-based chemistry, for say some other CO2 fixations?
Yeah, so I think it's a very good point, typically coming from somebody that is a molecular chemist, and I like that, yeah, because I think you have really paid attention to the literature. So what happens is that the field was dominated for quite some time by metal saline complexes, as you know, yeah? So mostly cobalt, chromium, to a lesser extent also aluminum-based saline complexes. However, as you have seen from the beginning onto the very end, if you want to valorize highly substituted feedstock, yeah, olefins, and subsequently their epoxides, you need to have powerful catalysts that can accommodate the coordination of a very bulky substrate, but also accommodate the incoming nucleophile to ring open and to basically advance to the final product. So these minor triphenolate complexes are ideally suited for this. Why? Because the system is not just a rigid molecule. It's actually quite flexible. This flexibility allows for, let's say, ligand deformations that allow for this incoming substrate to be coordinated and actually to be activated. If you now consider a saline complexes are typically quite rigid. Yeah, they are relatively rigid. So it is much more difficult to, one, coordinate a more sterically congested substrate, and second, to have at the same phase a nucleophile ring, let's say, doing the ring opening reaction. So this is one of the reasons, I think, why metal salins or metallosalins have not been that successful in a number of, let's say, substrate combinations, and why our system has been, simply because of the intrinsic flexibility of our system. And of course, you're paying some energy penalty, yeah, in terms of deformation of your ligand structure or your molecular structure. However, apparently this is not too much of a burden in order to make these transformations feasible. So I would say flexibility is a key feature of a complex. Yeah, it's almost the same as an enzymatic reaction where you have basically a floppy biocatalyst that suddenly gets, you know, its activity by rearranging all the different modules around the substrate so that it gets function and becomes reactive. Of course, our system is not that flexible, not that fancy, but it shares some of these, let's say, principles, I would say.
Okay, thank you, Aryan. I saw one question, Adam, I'm coming. I saw one question in the chat box. So it's from Jiyoung Lee from Denmark, one of our colleagues. Can we achieve net zero or negative CO2 emission with alkenes and epoxides for reacting with CO2? Is there any sustainable sources for them beside fossil fuel-based chemicals?
Wow, yeah, this is a question that we could, I can give a short answer and a long answer. So the short answer is, I don't think at this time we can achieve net zero emissions in these kind of operations, these kind of catalytic reactions. I think most of the reactions are basically net CO2 emitting, yeah, without a doubt. However, if we talk about energy, yeah, we want to use energy for our reactions, and we would be using renewable energy, we will probably cut down on most of the emissions anyway. Yeah? So I think the energy or renewable energy is a key aspect in order to make CO2 emissions as low as possible. The best way would be to consider feedstock that have, let's say, the appropriate functionalities, so that you have the lowest amount of steps in order to basically do your catalytic reactions. If you consider that you can do a catalytic reaction at low temperature and low pressure, maybe you can even use CO2 from the air, that would be ideal. But I think we're still far away of realizing that. It's, of course, a noble goal, but the short answer is that I think with catalysis we can come a long way, but we are not able to fully balance, let's say, the energy that we need and to make these, let's say, processes possible. So, yeah. Of course, sustainable resources, biomass will improve to a certain extent the carbon footprint, yeah, of a process. That's for sure. That's for sure. Yeah.
Thank you, Aryan. Yeah, Adam, sorry, please.
Yeah. First of all, thank you, Aryan, for this fantastic talk regarding CO2 chemistry. I am not an organic chemist. I'm a materials chemist. So I would ask a question about the catalysts and the recovery of these catalysts. So you had this TBD catalyst in one of your slides. So how difficult is the catalyst recovery, or do you have any work going on for immobilizing even organic catalysts?
Yeah, so in the polymer formation, well, actually the polymer breakdown, so if we take polylimiting carbonate, so we have a polycarbonate that is based on terpene and on CO2. Yeah, so we have a polycarbonate, and how to, for instance, recycle that polymer. We can take an organocatalyst, TBD, but then of course you are still stuck with the problem of separating the degraded polymer products and your catalyst. But we found in that particular case, we haven't published on that for particular reasons, but that we can easily separate our catalyst by precipitation. that's a very simplistic way of saying, yes, it is indeed possible. But a more realistic way would be to immobilize the TBD, which we have done. I've shown one example of flow catalysis, where you can immobilize that catalyst, you can put it in a packed reactor, and then basically under pressure, push your substrate through that packed back reactor, packed reactor, and in that way convert your substrates and separate directly your product from your catalyst. So I think immobilization is certainly possible. We have shown it, but of course it really depends on the catalyst that you have. So we have immobilized also our aluminum catalyst, but there are other problems that of course arise. So especially when you want to make use of CO2. So you would have basically three phases. You would have a liquid phase, a solid phase, and a gaseous phase. That complicates life to a certain extent. Not undoable. We have some results in that respect, but you would have to think about all the, let's say, challenges that you would have to solve. Right? So probably most of the reactions would then be diffusion control reactions, where you still where the rate of the reaction would be limited by the diffusion of CO2 to your active site. But apart from that, it's not impossible. It's not impossible.
Okay.
So yes, indeed, it is possible to immobilize and to do it. And the flow catalytic reaction that I've shown very briefly is a clear example of that. Yeah.
Thank you for the answer.
Yeah, Rob, please.
I would just like to point out that there's a question, a Q&A box.
Yeah.
But I have a very brief question. Maybe I asked it before. So I was wondering, Aryan, thank you very much again for the talk, for the nice talk. And I was wondering whether you are considering or whether you are trying to transfer your methods for synthesis of cyclic carbonates to coupling of carbon disulfide or carbonyl sulfide to make thioesters. Is that possible with your, for instance, the aluminum catalyst?
Good question. So the reason why we did not do that was there were other groups already, let's say, doing this kind of chemistry. Our focus was initially on CO2 because I think it has the strongest connection, with societal, challenges. We considered it, and I think in the lab we did some experiments. It did work. It was not totally selective, so we didn't optimize. So it is possible. But one of the things that we did do, which basically was a sort of a sidekick in essence, was making use of sulfur dioxide, SO2. Yeah, but that of course is much more easy to do because sulfur dioxide is not like the linear carbon dioxide unreactive. It's quite an active molecule. Yeah? So you can make that reactive. You can make cyclic sulfides and sulfates. And we did that. So we did that. We published one paper. So it is possible, but it depends basically, I think, on the interest that you have and the value of the product that you make. So yeah, thank you.
Thanks.
Yeah, Aryan, there is one question in the chat box. So thank you, Professor Aryan Clay, for your wonderful talk. Indeed, it is. And now the question is, for CO2 valorization, have you tried nano catalyst for such conversion, let's say CO2 to carbonates? If yes, in your experience, what will be the better catalyst choice for such conversion? Also, since food waste is a problem, have you explored the synthesis of nanomaterials catalyst derived from food waste and using it for CO2 valorization?
Okay, so several questions. Indeed, interesting. I'm trying to reread the question because it's a lot of text so that I get the essence. So nanocatalysts, so essentially, I suppose that these are heterogeneous catalysts, that you can get from any type of heterogeneous catalysis preparation. We have worked on some heterogeneous catalysts in collaboration with a group here at ICIQ. And especially if you want to combine the two functions that you typically have in a binary catalyst, that is an epoxide activator and a nucleophilic species, then you would have to incorporate those or immobilize those, let's say, on the same polymer in order to make that catalyst feasible. Yeah, so if you want to recycle that catalyst, you want to recycle both functions at the same time and not all the time in every new cycle add that, let's say, nucleophilic species to your reaction vessel. So we worked on that. We made a design where we can have both functions, and basically it works, and we see some deactivation, we can reactivate, and well, this is a typical problem of these kind of catalysts, but it does work. And we have made in a different exercise also other nano-based or heterogeneous catalysts. The downside is that you need typically higher pressure and higher reaction temperature. And we are not expert enough to make better catalysts based on our, let's say, pieces of Lego. But there are other examples in the literature where nano catalysts actually are doing great in CO2 conversion to carbonates or to other types of heterocycles. In terms of flexibility in your synthesis, so if you want to make a whole range of products with, let's say, difficult to make carbonates, then I think you would probably opt, at least for now, for a homogeneous catalyst. But if you're focusing on a bulk chemical like glycerol carbonate or maybe propylene carbonate, which have commercial value, then I think the choice would be very simple, and you would choose a heterogeneous catalyst because, of course, that is much more easily implemented into commercial, let's say, locations and in factories. So maybe I can answer that question in that way. If you want to do more complex synthesis, you choose, or you will choose homogeneous without a doubt. And for, let's say, products that have commercial value, the more simple products, you would choose a heterogeneous, or in this case, a nano catalyst. Then the second part of the question was food waste. I think it depends. You would have to define which food waste you would like to target. So one of the, I think, interesting targets nowadays are fatty acids, from the biodiesel industry. So if you take, you would hydrolyze your fatty acids off from your glycerol, then you would create fatty acids, and if they have unsaturation, they can make use of this unsaturation, making an epoxy group, and then you are very close to let's say, the carbonate chemistry. So that is something that we have done. We are also working on polymer versions of that, so to make polymers out of fatty acids, and we have already succeeded in doing so. So that's maybe not the typical food waste that you would consider, but I think it's the closest example that I can give for now. Otherwise, you can use, of course, terpenes. I've shown you one example of limonene during the lecture, limonene and CO2 to make polycarbonates. You can also use limonene to make polyesters or polyurethanes. So yes, food waste indeed is feasible. And if you want to do that, for instance, in flow, you can do that in flow, then you would choose a nano catalyst and not a homogeneous one. So it is that simple, I think.
Yeah. Thank you, Aryan. Thank you, Anu, as well, for your questions. There is one more question in the chat box. Is Beta-Alamine classified under primary or secondary terpene or terpenoid?
That is a very specific question. I'm not sure, so I have to leave this open. What I do know that we are probably one of the, let's say, few groups in the world that are working with this Beta-Alamine, because we are collaborating with this company. So we got samples, and it's not something that you can buy easily off the shelf from Acros or Aldrich or any other, let's say, standard provider. So yeah, I couldn't give any reasonable answer to this question. Sorry.
Yeah, then overall, thank you very much for all your lecture as well as all the discussion. Thanks a lot to both of you, to Aryan as well as Xiaodong, for your kind time, your patience, and answering all the questions.
Well, let me finish by thanking you again for the great lecture series, and just to end well, I'm looking forward to the next ones, obviously, and I think it's a great initiative. So thank you for including me in this program, and I hope that we can meet in person, in the near future again, because seeing all of you is really nice, but it's almost like looking at my television, at night when I'm watching the news, and it looks like all these people are out there, but it's sometimes difficult to imagine that, like in the pre-COVID time that we were chatting, maybe with a a glass of beer or something like that in a bar or in a restaurant about chemistry and about life. So let's hope that that will return. Yeah.
In Tarragona, Aryan. I would love to go back to Tarragona.
I'm sure you will. Don't worry. Okay.
It's a beautiful place.
Thank you. Okay.
Xiaodong.
Anyway,
Yeah, please.
have a great evening. Yeah.
I wish you too, Aryan.
Okay. Bye. Cheers.
Bye.
Bye-bye. Thank you.
Thank you all, also the listeners on YouTube or on Zoom. We hope to see you soon the next time in June.
Yes.
Bye. Thank you very much.
Bye.
Bye.
Xiaodong, thank you very much as well for your very nice lecture and all the time and all the discussions. We learned a lot.
Absolutely.
I think you're muted, Xiaodong.
Xiaodong, I think you are muted.
Yeah.
No.
Yeah, thank you very much for inviting me to give this lecture, and I also learned a lot from Arjan from your lecture series, and it's very good initiative, and I really looking forward to that you can continue with this.
Thank you.
Thank you.
Thank you.
Hope to meet with both of you very soon.
Yeah.
Have a nice evening then.
Have a great evening, all of you.
Yeah. Nice evening.
Bye.
Bye, Van.
Bye.
Bye.